It's my huge pleasure to introduce David Forsyth. He was my advisor at Berkeley, but he moved to Illinois, and so it's a great treat to have him here. And David has done a lot of really influential work on analyzing images and words and analyzing images and videos of people. He wrote the computer vision textbook that has been translated into Chinese, Japanese, and Russian. He has been on the program committees for various conferences and won Best Paper Awards and co-chaired major vision conferences. And in addition to this, he is also known as the baby-eating bishop of Bath and Wells. So this is David Forsyth.
Thank you, Sergey. So I'm delighted to be here. I'm going to talk, this is going to be a broad, impressionistic talk of a lot of work to do with looking at people, done with a lot of other people. Whoops, there we go. So I should mention Leslie Ikamoto, James O'Brien, Ryan White, Anthony LeBay, Okan Arakan, Deva Ramanan, Ali Fahadi, Nazlia Kisler, Alex Sorokin, Yotran, Yongtran, Wei Yan. These are people who've worked with me and made substantial contributions to what I'm going to talk about. Ali taught me a trick, which unfortunately I didn't use, which was he showed me that these talks turn up on YouTube. So the first thing I have to do is say hello to my children. And the second thing he said was, you know, everybody gets about the same amount of hits, except for the people who talk about pornography, who get 2 orders of magnitude more views. And in fact, years ago, I used to give a talk called Finding Naked People, which I thought, OK, that would be good for my hits. But all the slides were in plastic, so I couldn't do it. So why would we care about human motion as something to look at? So there are tremendous applications of understanding human motion in video. Some of them are sort of slightly disturbing 3-letter government agency type applications. For example, prosecution. The FBI might film people at truck stops for a year to try and figure out who is handing what illegal item to whom. And the problem with having a year of surveillance video is it takes a year to watch it. And there might only be 10 minutes that are really valuable for prosecution stuck in that video. Fairly obvious intelligence gathering applications. There might be crime prevention applications. So right now, Britain is plastered over with cameras watching what people do. And generally, that means that they might, if you're lucky, go and do it to somebody else somewhere else. And that already is seen as an application. Now, there are other applications that's sort of less 3-letter government agency. One is in human-computer interfaces. For 10 years or so now, people have been talking about interfaces that watch people and react to them in sensible ways. People's gestures might drive games. We've seen some of that becoming reality. You might think about whether you can interrupt someone or not, depending on their behavior or what they're doing. And all of this is still in the slightly iffy but plausible stage. Here's a funny one, and I'll show you some more about it. Architecture, the design of real buildings. As we move along, I'll show some examples that suggest how people behave in buildings is not terribly well understood, and the design rules have errors in them, and you can find interesting things out about how people behave in buildings just by looking at video. Another application for understanding motion involves motion synthesis. And this problem we'll talk about very briefly, but it basically says, make me a human motion that looks like somebody is doing this. And the reason you might want to do that has to do with computer games and movies. It's hard to put little people into PS3s, so you need to generate artificial motions. And the mechanisms for doing that are still fairly primitive. You might be interested in it from the biomechanical point of view. So there's some great work from Zoran Popovic, for example, explaining precisely why bird feathers have certain properties to do with the biomechanics of flight. What you do is you simulate flight, you observe flight, and then you say, well, this has to be true. And finally, if one does any computer vision, you discover that people are interesting. So years ago, I went and downloaded about 500,000 news pictures that I filched off a news site that didn't expect me to be doing something like this. And we were interested in using that and the captions of the pictures to learn things about the world. And we discovered that in 500,000 news pictures, there are no rhinoceroses. There are tremendous numbers of things that just don't appear in the news. Almost everything in the news is about people, and it's about small classes of people who just appear again and again. People are interesting. Okay. So what are the themes of the talk? Now, some of this talk is sort of a core vision talk about core vision issues that we don't fully understand. There's some very, very nasty issues in this question of watching people. One of them is we don't really understand how to do activity recognition because we don't know what the answer means. There isn't a clean taxonomy of activities. So we've got lots of papers that say, you know, take some features, stick it in a classifier, and it'll tell you the difference between walking and running. It's a big favorite these days because actually it turns out you can do that rather well. More generally, when you want to think about what are people doing, it turns out that you don't have a particularly good vocabulary for describing that. We don't have a tremendous number of accurate terms, and we say, well, classify into one of these, and you'll understand what's going on. And that problem turns up again and again through difficulties in transducing signals, through difficulties in knowing what to do with signals. It's the main source of difficulty here. The other thing that goes on, and that's part of this problem, is that activity composes in quite complicated ways, and I'll show some of this. Big theme, current signal representations are unsatisfactory. We know two of them. One of them says, track the person, figure out what they're doing in 3D, and that has problems. The other thing says, look at some image patches, look at the motion of those patches, and classify based on that, and that too has problems. So let's start with thinking about activity. A big thing that turns up in human motion is composition. So why is that a good thing if you're a human? Well, if you know how to do one thing and you know how to do another thing, you can put the two together and you can maybe learn something new. You can scratch your head while you're walking with either side, and you don't have to be walking to scratch your head, and that is useful. It gives you planning flexibility and control flexibility. Now, as I shall show, we can join up human motions in time to make very good new motions, as I suggested. You know, you walk, and then you stop, and then you walk, and we can do that from the animation side as well as the human side. We can also join up parts of motion across the body, but it doesn't always work. These two joining up processes, which I will demonstrate, are sources of fearsome complexity and understanding. So here's a problem. Produce a human motion that meets some constraints and looks good. If you can solve this problem, there are all sorts of applications, as I talked about in computer games, and there are some traditional solutions. One of them is you hire an animator and make him do it, and that's still the best way of getting a good answer. Another way you could do it, which is now quite strong and seems to be sort of the way to do it, is a non-parametric strategy, which says take a bunch of observations and join them up. Why do we care? Because it will expose to us some practical properties of human motion. So here's a method for making new motions from old ones. I'm going to go out, I'm going to use a motion capture system to measure the configuration of the body for people moving. Motion capture systems place sensors on joints. They hang large numbers of cameras and various other infrastructure in the ceiling. They produce three-dimensional measurements of those sensors, and those measurements are turned into a reasonable kinematic representation. Now, I've done all that. I've got a 3D representation of the body. What I'd like to do is to be able to make motions I've never seen before. How am I going to do that? Well, I'll make a little graph, and the graph I will make has each 3D representation as a node. And then if I saw this frame after that frame, when I made the data, I'll stick in a directed edge. And then I get some directed edges. Now, that's not terribly interesting because it says you can play the sequences you've already observed. Now what I'm going to do is I'm going to say, well, if this frame and that frame look a lot like each other in terms of acceleration and velocity, then instead of going from here to here, you could go from here to there. And I'll stick in a directed edge there as well. And I can compute whether that's the case by comparing differences. So I stick in a whole bunch of these new computed directed edges, and then I say any path in this graph is a motion, and various people argue in various ways about different algorithms for finding paths in this graph that meet various constraints. We don't care about those arguments. What we do care about is you can get really nice motion out of this business. So fairly clearly, I didn't observe this. Less clearly, it's about 14 little pieces of motion sewn together in different ways. Why is it less clear? Because it actually just looks like seamless movement. Okay? What that means is this process of joining the pieces up at least works as a model, can be used usefully, and should be something that one has in any attempt to interpret motion. Now, I said motions were compositional. They join up, and we joined them up across time. It's reasonable to believe you might be able to join them up across the body as well. So I said, for example, I could walk and scratch my head with one hand or scratch my head with the other hand. Now, one way I could learn about walking and scratching heads is I could take movies of both events, but that would get dull after a while because of the complexity that is generated by this composition. What I'd really like to be able to do is to have a model of walking and scratching with one hand, and then know that you could cut this arm off and this one, move the arms across, and scratch with this hand instead. And a natural thing to do is to say, well, why don't we take some of this motion capture data, cut the arms off some motions and attach them to others, and build new motions? Does it work? And the annoying answer is sometimes. So here's a little red guy running, and here's a blue guy doing something else, and we cut his arms off, stick him on the red guy, and it looks fine. Right? Now, that is, again, you should see this as a source of fearsome complexity and recognition, but great flexibility and animation. It's a dangerous source of flexibility, though. Here's a little blue guy doing something with a football uniform. Here's the red guy doing something. We're going to cut off the blue guy's top and stick it on the red guy's legs, and it doesn't work at all. Okay? Why does it not work at all? Well, in fact, there are not many terribly good theories about that. Basically, what seems to be going on is you expect to see correlations between motions across the body, and they're not there, and that motion is mechanically incoherent in some way. Right? So we've established that motion is compositional, but there's more to it than that, and that is where we leave animation. So what we really, really want to know is, what are people doing? I got a movie, I want to say, what are people doing in the movie? The big difficulty here is, this is a Rumsfeldian statement that I just can't resist. It is not known what needs to be known. What do you need to know about the video to be able to answer the question of what are people doing? And in fact, there are several different, slightly counterintuitive answers. So the three big answers about signal representations. One of them is a recent answer, which says just basically spatio-temporal motion features. That's work due to Laptev and Perez. I'll talk about it in a second. And the other two are fairly natural. One is to say, OK, figure out where the people are in the movie, track the bits and pieces of their body, work out where those are in 3D, and interpret that using some form of model. And the other thing you might do is say, well, we know the big mystery of computer vision over the last 20 years has been to understand that 3D doesn't matter as much as you think it does. So maybe it doesn't matter, and what we'll do is we'll figure out where the body is in 2D, and we'll reason about that to come up with features that tell us what the person is doing. So firstly, some counterintuitive stuff about the right signal. So this is work by Ivan Laptev and Patrick Perez, and they took a movie. I can't remember what the movie was called, but it's always known in the vision community as Smoking and Drinking, because it consists of a bunch of people who sit around and smoke and drink. Okay? And they talk to each other as well while they're doing it. What we'd like to be able to do is to tell when someone is smoking or when they are drinking. And these are nice and interesting activities because they're complex. They appear in a bunch of different forms. People actually do them. And it might be the case that you could think about tracking the body. But there's another thing you can do. In a movie like this, typically the actor is framed in a particular way. Either there's one guy drinking like that, or there are a bunch of guys drinking, but there's not much background. When you drink, when you lift your hand up like this, you generate very characteristic motion fields. So what you might do is say, look, what I'm going to do is take windows in the image, simply compute a spatio-temporal feature out of those motion fields in those windows, basically figure out the motion for a little bit in the future and a little bit in the past, put that motion field together, turn it into something like a SIFT feature, and sling it into a classifier. Can you find what people are doing like that? Answer, yes, embarrassingly well. So over here, these are the top 20 returns from frames, a collection of frames of the movie where they said, return drinking. And you'll see the ones that are wrong are done in red. And you see, on the whole, they're getting it right. And these are the top 4 from that list, so you can get a closer look. Just by looking at motion features with no other information, no segmentation, you can tell whether a person is smoking or not. You can tell whether they're drinking or not. Okay? This trick has been used more recently to look at other activities as well. I managed to leave the reference behind. So here's another little mystery on the it's not known what needs to be known line. So about 4 years ago, Wei Yan and I wanted to do just a little public observation study. He was doing an architecture PhD, architecture as in sort of real buildings and fountains and stuff like that rather than little bits of computer. And he was doing an architecture PhD, and what he wanted to do was to understand the design rules by which you built open public plazas. There are a bunch of rules, and those rules are set up by observations that were made with film back in the 70s, I believe. So what he did was he stuck a camera about here, looking down on Sproul Plaza at Berkeley, and then it turns out that it's quite easy to segment the back of people's heads from backgrounds if you know what the background is. And if you segment the back of their heads, you can usually match up the backs of heads as well. So you can build a real simple tracker that just says, well, here's a person, here's where they are in the next frame, here's where they are in the next frame, and it's reasonably accurate. Now, there are 2 things you learn from this. One of them is that people are a lot like ducks, which is the first person at a fountain takes quite a long time to arrive. The second one comes very shortly after the first one. So he did a plot over here which says number of people after the previous number. So what we mean by this is where it says 1, that's the time it takes for the first person to arrive. And where it says 2, that's the time it takes the second person to arrive, conditioned on the first one's there. So what that means is the first one takes about 6 minutes to arrive at the fountain from when the fountain first empties. And the second one is there less than a minute later. And after that, they keep coming in. Right? That was known. That's an established feature of architecture. The second person comes fairly quickly to sit down. What wasn't known is a little mystery that you can actually see, and it's in the concrete on Sproul Plaza. If you look at these tracks closely, attending to the fact that the tracks are the heads of the person, which is why they're up sort of that way. It's not that people like to walk into trees. It's we're tracking the top of their heads, which is up there. You will see there's a small concentration of tracks about there. Usually what people do with a plaza like this is they come in on this side and they go out on that side. Sometimes they come in on this side, they go out on that side. Occasionally they'll do that or that. If they go down the stairs on this side, they go past this point. Okay? Why? I don't know. And I couldn't find anybody else who could explain it to me either. And I think it's one of those many little mysteries of human behavior that are mysteries because we simply don't have the observation data yet or the techniques. But you can confirm that this is true by going to the location. You can actually see it in this picture. There is a stain and wear pattern on the concrete over here. And that concrete, if you go to the location and look at it, that concrete is significantly more worn than anywhere else on the stairs. Right? Very simple public observation using almost no features of people have already shown a mystery that, of which I'm not aware of an explanation. So let's talk about more complex features for a bit. So tracking people is hard, but you can do it. And there are big advantages for thinking about aspect and composition, as I will show in a second. There are problems with accuracy in tracking, and we'll see them, but there's recent work by Ferrari and Zisserman. Now, why is it hard to track all the bits and pieces of the body? By the way, the one person who's been engaged in kinematic tracking, whose name doesn't appear on the slides, of course, is Sergey, who built one of the very early versions of the tracker that I will talk about. I have some references on tracking slides, but it's a huge literature. And I wrote a review, I don't know, a year and a half ago, which is on my webpage and has 450 references. If you want to know about tracking and motion synthesis, that's sort of the first place to start. Why is it hard to track the body? And when I talk about track the body, I'm saying kinematic tracking. I want to keep I want to keep in track with the upper arm, the lower arm, the upper leg, the lower leg, the torso, and any other bits and pieces that I can track. First thing is, it's hard to detect people. It's genuinely very difficult to detect people in pictures. It's getting easier, but it's still hard. And it's hard because in different pictures, they look different because they rearrange their bits and pieces in funny ways. Firstly, you get changes in pose and in aspect. Over here, you will see that the people are getting in front of each other. And knowing just how many people are in this collection, I think it's Australian rules football. You're allowed to kick one another when you do it. Figuring out how many people there are in this tangle is really not easy. Counting the legs and dividing by 2 doesn't do it. And there's, of course, tremendous variation in what people look like, what they wear, the shapes of their body, where all the bits and pieces are. So that makes them hard to detect. People also move very fast, and they can move quite unpredictably. So your hand is a good example of something that can move fast. There's a great pack of muscle on your shoulder. Your hand is at the end of a long lever, and that means we can generate big forces here and big accelerations there. That means that dynamical models of what the body does are probably not terribly useful unless you look at very, very high sampling frequencies. And that, in fact, has been borne out by experience. The other thing is that many body parts are small and tend to have poor contrast. So the things you might like to know about, like upper arms, are small, which makes them hard to detect. And I'm not wearing the right shirt, but if I was wearing a long-sleeved white shirt and I waved my arm in front of my body, all these bits and pieces would have almost no contrast. So there are real serious technical difficulties here. One can build trackers, and one can build trackers now that work OK. Spectacularly well is hoping for a lot, but OK is a possibility. And the trick to building the tracker, this is a line of work, as I say, that started with Sergei's work and then went on with work by Deva Ramanan and Andrew Zisman and a variety of others. The trick to building these trackers is to know that even in quite short video sequences, people take lateral walking configurations, which are highly distinctive. Somewhere in a short video sequence, I'm going to look like this. Why? I don't know. It's just an empirical observation. It happens. You can detect that. And you can detect that. You don't have to detect it particularly reliably as long as you get one in the sequence for each person. And if you do get one in the sequence for each person, now you know what that person's arms and legs and head and torso look like. Why? Because you've detected the person. You know the legs are over here. These pixels are on the legs. You also know a ton of pixels that do not look like the arms, the leg, the head, whatever. So you can build little discriminative classifiers that say, these pixels look like the leg and these don't. And then I'm going to take each frame and I'm going to say, well, there might be some leg pixels over here, some head pixels over here, some arm pixels over here, and some torso pixels over there. Once I've done that, I know that I'm going to get a whole bunch of other stuff wrong. So those are not arms, those are not arms, those are not heads. But the second distinctive feature of the body is the bits and pieces join up in particular ways. And I can use a device from the vision literature known as a pictorial structure, which is basically just a souped-up tree-structured Bayes net. I called it a hidden Markov model until people smacked my hands for doing so. And I can link these detects up into the correct spatial structure. So these legs, that head, that arm, and that torso all belong together. Once I have done that, I have a detection procedure that I can just apply to every frame. And that, in fact, will give me a track. It'll give me another track that is quite neat, because if there are two people, another property that is neat, if there are two people that I detected and their clothes are different, I know the difference between them. So this tracking procedure works rather well. So she is running, as you will notice, from bright light to shadow. And we still know roughly where her bits and pieces are. And we've got a reasonable sense of what the body is doing. And here we have, now what I'm showing is a report of the covariance of the track. So instead of drawing where the arms and legs are, I'm drawing, if you like, covariance ellipses for those arms and legs. And there's somebody doing something. What is that person doing? Skating. It's figure skating, yeah. Can you tell the gender of the person? Me and David Ramanan are convinced that you can, but nobody else seems to agree with us. So it's female. And in fact, yeah, it's a figure skater. It's a female figure skater. And as this sequence runs, what we have here is a fairly decent representation of where the bits and pieces of her body are. It's not perfect, but we know where the bits and pieces are, and we can probably use that. And this will go on forever. It's a long sequence of a skater. I'll show, at the end, I'll run it up while we discuss questions and the like. OK, so what could you do with that? Well, one thing you could do would be you could try and reason about where the body was in 3D based on where it is in 2D. And then I've got this 3D stuff. I've got a bunch of 3D labeled data I can classify. How would I reason in 3D? Well, there's a trick which is not as widely known as it should be in the vision community, which says, actually, if you see a body in 2D, up to some discrete ambiguities, you know where it is in 3D. And the reasoning is roughly like this. Almost always, you see people in orthographic views rather than perspective views. Sometimes you see them in perspective views. It's usually a famous person holding up a hand to keep the paparazzo from taking a picture, right? But usually you see the body in roughly orthographic views. For most people, under most circumstances, you know how long the body segments are, right? There's a factor about 1.5 between tall people and short people here, and that's of no significance at all. So if I know how long something is, and I see it in an orthographic view, the reason it is shorter than it should be is because it's been foreshortened. And that tells me the cosine of the angle between the viewing direction and the thing that I'm looking at. Now, there's a twofold ambiguity over here, the status of which is not terribly well understood, to be honest. But I can go, using this line of reasoning, and this has been established for, I don't know, 8, 9 years now, from something which says the ankle is here, the knee is here, there's another ankle, there's another knee, hips, wrist, elbow, etc., to a 3D representation. And small changes in scale give me slightly different 3D representations, but I've got a reasonable configuration of the body. I won't speak to this slide, but I leave it here. There's a great deal of confusion about how ambiguous this lifting process is, which is still unresolved and is probably fertile ground for science. OK, so now what I want to do is name activities. So what am I going to name them with? Well, the first thing I could do is I could choose actions with names. So I could study gymnastics, or I could study Tai Chi or ballet, and there's a name for a particular activity, and we're OK. But we're really interested in everyday motion. So the problem I'm going to run into is there's never really enough data of everyday motion to learn good models. So what could we do? One thing we could do, and in fact, sorry, I put in an extra slide here and lost my rhythm. There just isn't enough data to learn models from video. If you try and learn generative dynamical models, you get clobbered, and you get clobbered because there are too many dynamical parameters. They're hard to learn, and you don't have enough data, or there are the model is insufficiently expressive. And if you try and learn discriminative models, you'll also find out you have not enough training data to get good performance, because people change aspect and clothing and the like. OK, so what could we do? Well, one thing we could do would be to label motion capture data. Numerous people have done this, mainly using a collection of motion capture data released to the research community by Electronic Arts about 6 years ago. Georgia Tech is producing a bunch of this data as well. There are some very desirable features of a labeling that we've already seen. One is it should be composable. So if I take a sequence, I should be able to label a frame waving, and I should be able to label another frame running and also waving. So I'm going to have tags that compose. What I'm going to do also is say, I'll guess the best vocabulary I can, and I want to be able to relabel very quickly. And it turns out you can do this. How do you do this? Well, what I'm going to do is I'm going to choose a bunch of different vocabulary items: walk, run, jump, stand, carry, wave, turn left, turn right, labels like that. I'm going to take my motion capture data, and then I will label some examples and train a little classifier. And then I'll see, does it label everything else right? And I'll do that for walk. And if it doesn't, it turns out to be very easy to display all the labeled motions. And you say, well, that one isn't walking, move it to there. That one is walking, move it to there. Retrain. And you keep doing that until you do walk well. And then completely independently, you go and tag the data for running. And then completely independently, you tag it for jumping. And completely independently, you tag it for standing. Now, there could be problems, because you cannot, in fact, stand while you're running. And we will just ignore those dependencies completely as being a sort of second-order thing. So now we go and label. We've got 13 bits. What can we do with it? Well, the first thing is we can tell little animated creatures what to do because we know what they're doing. So this little guy can be told to run, then jump and catch the ball. We tell him that, and lo and behold, he does it. That's convenient, and it's got applications. But we're not going to concentrate on that. Instead, I'm going to take the fact that I can do that problem and use it to label data. So I have a bunch of annotated motion capture data. I have some video. I went and tracked that video. I can take that 2D track and lift it up to 3D. So I know where the body is in 3D. At the same time, I did a bunch of annotation. I built an annotated 3D motion library. I have a motion synthesizer that will build me good human motions that follow a sequence of labels. And I demonstrated its output, but I didn't describe how it worked. Now, what I could do is say, look, here are a bunch of 3D lifts. Build me a motion sequence that lies very close to these lifts in 3D, and then tell me what the labels are. And we will do that. Does this work? Sort of OK. I think you should be reminded, this is 4-year-old work now, so things are a little better. You should be reminded of my colleague Robert Walensky's remark that it's bloody at the cutting edge, meaning we've got a rough idea of what these guys are doing, and we've got a rough idea where they are, but the labels aren't by any manner of means perfect. But we're still not doing as well as we could on this question of composition. Okay. So what I'd really like to be able to do is have much more complex three-dimensional motion models. Right now, my motion models are string things together in time. And what I'd like to be able to do is to string them together in time and across the body. So I know what an arm looks like when somebody is walking, and I know what a leg looks like when somebody is walking, and I know what an arm looks like when somebody is waving, and I know what a leg looks like when somebody is waving. So previously I said, from the point of view of an animator, cutting things up across the body and reassembling them is not necessarily a good idea. When I cut the blue guy's arms off and stuck them on the red guy's legs, sometimes it worked, sometimes it didn't. But for interpreting a signal, I should be OK here, because people don't move like that. I'm going to see the signal. It's really generated by a person. The fact that my model can sometimes do something weird is less of a problem. So what I'm going to do is this. I'm going to take all that motion capture data. It's labeled, so I've got arm walk models. I can build arm walk models. I can build leg walk models. I can build arm stand models. I can build leg stand models. Then what I can do is take those little short timescale models and join them up to each other. So if you're an arm and you're walking, you can do your arm walk, and then you can join to another arm walk, or you could join to an arm wave. And then I can string them together across the body as well. So I can say, well, I can take the product space of this finite state model, essentially take an arm walk and a leg wave, and join them up, and a leg walk and an arm wave, which is likely to be much more useful, and join them up. And when I do that, I come up with a sort of holy grail, which is a very big finite state model of what a motion could be, with very few parameters to learn. And the parameters I need to learn are, what do the little local models work like? This is modeled after a trick that you see in speech rather a lot. You learn phonemes, and then somebody else writes down how phonemes form into words. So then I'm going to see, so I say I've got many parameters in this, many states, but few parameters. I am going to see material from a tracked body. I'm going to lift bits and pieces of each quarter of the body into 3D, and then I'm going to join them up to be a consistent body in 3 dimensions. Now, why would I go through all this trouble? Well, the answer is, if I build a model of this form, I can query for motions I have never seen examples of. Right? My model is capable of generating a sequence where the leg walks and the arm walks, then the leg walks and the arm reaches, even if I haven't seen that. And furthermore, by adroit manipulation of finite state models, I can take a video sequence and I can say, what is the posterior probability, based on all the learned parameters and the like, that in this sequence there is a sequence that looks like that. Anything generated by a finite state, one of these combinatorial things. And what I could do then is search for things I'd never seen before. So what did we do? We took a bunch of people jumping around in our laboratory. We gave them instructions: crouch, run, jump, jack, run, carry, etc., run backwards, wave, run, jump, reach, walk, stand, wave, walk. We got sequences of reasonably complex motions on fairly easy backgrounds. And we then said, what we want to do is search for these things. So these little bars are different colors depending on the individual. So they're wearing different clothing, and they have different body shapes and the like. And then what I'm going to do is I'm going to take my sequence, and I had about 75 video sequences. So these are the 75. And when I do a query like walk, stand, I want a sequence where somebody's walking, standing, then waving, then walking. So what I'm going to do is rank all of those 75 sequences by this query, and then put a little mark over here every time there's a relevant one. So in this case, the first two are relevant, and then there are a bunch that are not relevant, and then there's one that's relevant, and then there are a bunch that are not relevant. So in a picture like this, if it was working perfectly, then all the color would be on the one side. So there are two things. One is it works okay. Can I compare numbers with other numbers? No, because there isn't anything else that does this. Two, the clothing that people are wearing doesn't seem to be a big issue in the reason it doesn't work. We'll see why some things go wrong fairly shortly. OK, there is a second thing that's quite neat about this 3D reasoning, and it's important, which is changes in aspect don't, on the whole, cause performance of this kind of query to fall off. So what am I going to do to establish that? I'm going to take a bunch of sequences like wave, reach, jump, jack, jog, jump, etc. I'm going to do queries on those, and then I'm going to ask what's going to be the mean average precision for those queries as a function of the angle that the camera makes with the body. I'm going to view the person from different viewing directions. I'm going to ask what happens to the retrieval. And the answer is, it's not perfect at any of the angles. Some of them are better than others. But we don't see a catastrophic failure as the aspect changes. Why is that? Because we can get into 3D and we can reason in 3D. And when we're there, aspect isn't that big a problem. Okay. There is one major problem here, which is these trackers, although they work, are by no manner of means perfect. Right? And you can see this guy in the background over here has grown an extra leg in a fairly uncomfortable spot for an extra leg. And you expect that to happen regularly across frames, and it's a major nuisance. And one would, given this pace of the development of the state-of-the-art of trackers, it's a nuisance one's going to have to live with for some time. Right? And it generates all sorts of noise, and it probably explains why, even on relatively simple queries, the retrieval results are at best OK. So what could one do? Well, the alternative thing I could do would be to take that whole discussion of appearance seriously and use that as a cue to what people are doing. And we know some things about this. One of them we know is where you are can be a very powerful guide to what you're doing. Right? There's certain things you do only in certain places. Right? There are other things where if you're there, it's pretty clear what you're doing, even though it's not absolutely certain. The second thing we know, and this is sort of very well established, is the configuration and motion of your body in flat images do seem to be quite distinctive. So there's lots of history in these issues. And what you might do is say, well, what I'm going to do is take a video. I'll put a little box around a person. Having put the little box around the person, I'll build a feature that essentially looks like, where do I think the bits of person are, which is not absolutely accurate. Where do I think the motion is? Take these features and bucket them in the usual way of sift features and histograms. Look at this property over several frames into the future and several frames into the past with reduced precision as you look far into the future and reduced precision as you look far into the past. Rack up a big appearance feature like that and then stick that into a classifier and say, we'll classify the motion based on what you look like. OK. Again, these appearance features are quite well tested. The one I'm describing is one we did, but there are a fair number of appearance features out there, all sort of along the same lines. There are a bunch of data sets. One is due to INRIA. It's called XMass. There's one at Weizmann. There's one at Maryland. We did one as well. You typically have a bunch of actors, a bunch of actions, a bunch of sequences. Most of them have one view, but the XMass has 5 different viewing directions, and that's worth keeping track of. So if you do this, now I've got sort of discriminative results for everything on everything over here, and it's a table full of numbers. We only really need to pay attention to a subset of these numbers. One is, if you do a reasonable job of signal and the like, one nearest neighbors with metric learning will do extremely good classification on these data sets. There are a variety of different discriminative tasks. You could leave one person out. You could leave one sequence out. You could leave one action out, et cetera. But generally, what you want to be looking at here is all of these numbers are pretty high. You can take those features, and you really can say what people are doing based on those features. If you do that, you can, in fact, go and mark up video automatically. So mysteriously, we possess a whole bunch of badminton video. And you can sit down with this badminton video. You mark the little blue guy and the little red guy. And then what I'm going to do is I'm going to classify what he's doing. And for the blue guy, that'll give me a little dot over here. He could be running, walking, hopping, jumping, unknown motion, forehand, backhand, smash, unknown, shot or non-shot. And then I'm going to, in gray, mark up ground truth. And blue will be marks of what he's actually doing. And the main thing here is the blue sits on top of the gray most of the time. So I've got a fairly good idea of what this fellow is doing, and I've got a fairly good idea of what the other person in the sequence is doing as well, right? In this relatively restricted vocabulary. Now, the problem with this representation of activity as a pure appearance thing is, of course, people look different when you see them from different directions. So this XMass data set is intended to emphasize this fact. You get a whole bunch of different cameras, and somebody walking or somebody doing something in camera 0 might look like the top row, but in camera 4, they look very different indeed. Camera 4 is overhead, camera 0 is somewhat lateral. So to hammer that home, what I'm going to do is I'm going to go and I'm going to learn a model from camera 0, and then I'm going to test it in camera 1. And I'm going to ask, how often do I get the answer right? And the answer is not very often, basically. Right? So somewhere between 40% of the time when I'm doing well and 8% of the time when I'm doing very badly indeed. So all those nice 90s and 100s and stuff have just put in the dust. It's hard to directly learn a model from one view and then apply it in a second view. Now, what might we do about this problem? Idea. What I'd really like to do is to use features that are robust to changes in aspect. And in fact, I'm going to encode aspect explicitly in my discriminative procedures. So how would I construct those features? Well, the nice thing about objects in general, or about the visual world in general, seems to be that comparisons behave rather better under change of aspect than exact features. So it might be a bit difficult to say what this exactly was, but the fact that this is like that seems to hold as the aspect changes. I'm sorry, this is one of these annoying animations that I can never quite purge from my slides. These two look like each other in this view, and they also look like each other in that view. These two look like each other in this view, and they also look like each other in that view. And that suggests a feature representation that is comparative. Instead of saying, this is what this person looks like when they're doing that, you'd have a whole bunch of examples, and you'd say, they look like this. And that behavior might behave rather well under aspect. You can think about this as taking the space of appearance examples and splitting it. So over here, what I'm doing is I take a bunch of known examples. I'm putting a random split in that bunch of known examples. And I'm going to take my unknown objects, and I'm going to describe them by how they fall in those. Sorry, my animation seems to have gotten mangled. Whoops. Come on. Here we go. So that red tomato is an unknown object, a new thing for which I want to compute features. Here is a separation of my space of objects into two parts. Roughly, the semantics are round and not round, although round is perhaps a strong way to talk about it. I'm going to take that tomato and say, by the green split of the space of objects, the tomato, in fact, is on the not round side. Not sure why. Oh, it's on this side, on the round side. By the green split, the mug is on this side. It's more like these things than it is like those things. That comparison I will use as a feature. I will then tag training examples with an aspect variable, which I will have to estimate, and I will estimate a classifier and an aspect variable. What happens? Remember, ignore the first two columns because it's a little piece of internecine fighting about different mechanisms of feature construction, which is not relevant to us over here. All those 8s and 16s and 38s suddenly turned into 80s. So what we can do is learn a model of what the person is doing from camera 0 and classify from camera 4 rather accurately. OK, now, question. What about composition in these appearance features? Now, we're almost at the end of the talk, which should cue you to the fact that this blank space here has semantics. It's not that I didn't know what to, well, it actually is I didn't know what to put there. We simply don't know the answer to this question. Okay. So, conclusions. The fact that we don't know what labels, what the taxonomy is, the structure of the labels of motions, the fact that we don't know that is a major nuisance. It's a nuisance generated by this composition. Motions are really complex. Your body can do a lot of stuff, and it's usually related to what you're doing. If it were not for this issue of taxonomy and composition, appearance methods would win hands down because they actually perform, as we saw in those numbers, rather better, and I was able to turn aspect into a nuisance rather than a deal breaker. So, what do we need to say about activity? Should we name it? Should we be reasoning about goals? Should we be reasoning about intentions? And what are the objects nearby? What do they contribute to what we understand, and how do we use it? These seem to me like the very big open questions. Finally, actually, given this has been publicized, I should stand in front of these words because I looked for a synonym for fool's paradise. Right now, in computer vision, the object recognition technology is actually quite well developed. There are lots of classifiers that will tell you this is a motor car and this is a person, right? They're not that good at dealing with things that are unknown, but quite like things they've already dealt with. So if you know about cars and you know about motorcycles and you know about buses, if it's a car or a motorcycle or a bus, you're OK. But if it's a truck, you're dead meat. And you shouldn't be, right? And I think that problem is the same problem as this absent taxonomy composition problem, and object recognition community is about to run into it in a big way. Fool's paradise was the best phrase I could find. It sounds a bit pejorative. There is, of course, a bonus question. So if you look at this little animation video, you'll notice that the characteristics of motion tell you a great deal about the individual. Okay, so this exaggerates that it's an animation and the like. But this guy doesn't move even remotely like the other guy does. And you know that that is true for people. Most of you should be aware of the fact that you can tell who is coming to your office by listening to the footsteps on the floor outside. You know who it is. Why? Because people, everybody has their own central nervous system, and it leaves profound marks on the motion as you move your body. You should be able to recognize people from the way they move. We don't know how to do that. And that's the end. There's my, or rather Deva Ramanan's little ice skater doing her stuff. She'll do it all the way through. I think I've run a few moments long, but I'm sure we've got time for questions.
So there's a microphone if anybody else has questions.
I'm sorry, question.
So about these patterns of exploration of the people in the square when they found it.
Right, right.
I know people have been working on modeling type of exploration by other mammals like rats in the environment. I was wondering if there is any relation between different animals.
So I think I want to turn it around the other way, which is simply being able to watch and track things, whether they're people or other things, in video, can be tremendously helpful and revealing. There's some nice work going on in UC San Diego where people have been tracking mice. Right? Why would you track mice? Not because you care so much about what mice do every day, but your canonical medical experiment is to feed something to mice and then see whether they die or they run around a lot or whatever. So how do you do that? Well, either you make some poor graduate student sit in front of the cage and count how many times the mouse scratches itself. You just film the thing and watch how it moves around and what it does. And it turns out just keeping track of roughly where the mouse is incredibly informative. There was a bunch of work at Caltech on phenotypes in Drosophila. So these are these little fruit flies, which basically they do different mating dances in different ways depending on what genes they have and some sort of biological thing. How do you know? Well, one thing you can do is you put pairs of Drosophila into a lot of translucent boxes. You film them from above, and then you cluster the spatial tracks that you see, and that's very revealing about the behavior. I think it's important to notice that apart from the stuff with cell phones and little worn devices that's been going on recently at MIT, there is not much mass observation of what people do in public. Based on my experience of surveillance video, mainly they walk from point A to point B, and that's another source of complexities of its own, because what you really want to be able to spot is the unusual stuff. And the problem with the unusual stuff is you haven't got very much of it. But yeah, there are lots of applications. There's work in, I think, chimpanzees, maybe. I heard about it yesterday, this morning, so I'm not all that switched on with it. But there's similar things. Where you are tells you what you're doing.
So I have a question. When you talk about composition, so it seems like there are some things that you can compose. Like, for example, what one leg is doing, you can compose with what another arm is doing. But some things are not quite so, are talking to each other.
I believe that to be true.
So the question is, can you figure out automatically what you can compose and what you can? And it comes up in object recognition as well.
Every time I've tried, it hasn't worked, I think, is the best I can say about that. So yeah, there's a big, nasty issue there. I showed you that example of good motions and bad motions. The bit that I suppressed, in the interests of time, had to do with the fact that, the obvious thing to do is to build a classifier and say, tell me a good motion from a bad motion. Stick it at the end and just throw away the bad ones. The downside of that is that classifier doesn't work. And there have been 3 quite good attempts to build classifiers. There was some stuff by Ren, I think it was, et al. In CMU a couple of years ago. That was sort of okay. It's a little bit better than chance. And then Leslie Ikamoto built one that was a little bit better than that one. And the way it worked was it looked purely at foot skate. Right? So it said, when you generate a motion like this, does the foot skate on the ground? And we know that it shouldn't. But we also know that what's going wrong in sequences like the one I showed you has nothing to do with foot skate. So the problem is you can't just engage in a statistical fishing expedition because there are too many variables to be able to be sure that you actually know what correlations are important based on a reasonably sized data set. Remember, these frames are several hundred variables each. So who knows whether the left arm is correlated to the right leg. But having a theory, though, would be extremely helpful. I'm not aware of one that's viable at present. You might describe a theory in terms of goals, of intentions, of planning, but it's not there yet. Yes. Right. So let me read the question back, because there may be people who can't hear it. The question is basically, there are large quantities of actions that have a kind of parametric structure. You can reach for different places in space, or you can hit things harder or softer or whatever. And how does that play into representations of action and intention? Well, I wish I knew the answer. The best answer I know is there have been some small-scale domain studies of specific parametric actions. There's a little bit of work on animating these parametric actions, which is something you can do fairly well if they're ballistic in structure. So something like reaching is essentially a ballistic movement. Then it doesn't work so well if there are collisions that occur during the action or contacts or things of that form. So if you think about striking something, if you think about hitting a ping pong ball with a bat, because the collision is a dominant part of the action and they're very fast accelerations, right now we don't have really good parametric models that allow you to do that or that. From the recognition side, I'd say the game is pretty much open. I know there's some work about parametric classes of gesture. The fish was this size, the fish was that size. But I'm not aware of a broad theory. I would regard that as an opportunity rather than